Hello Proviso students, and welcome to lesson 3.2 video notes, understanding relations and functions. You will find these notes correspond with pages 115 through 126 in your math workbook. So in lesson 3.2 we have three learning objectives. The first one is I would describe a relation. Second, I would describe what makes a relation a function. And the third one is I will be able to apply the vertical line test to determine if a given relation is a function. These are the three things you need to be able to do by the time you are done working on this lesson. And those three learning objectives could be nicely tied together with this essential question of how does one represent relations and functions? And that's what we are ultimately working on. In this lesson, there are four key vocabulary terms you will learn: relation, function, domain, and range. The first vocabulary term we're going to talk about is relation. Your author states that the relation is a set of ordered pairs x comma y, where x is the input value and y is the corresponding output value. And that definition is listed on page 115. So let's look at an example of how we could represent a relation. I have the daily specials from a local submarine sandwich restaurant. And on Monday, their special is the king meatball. Tuesday, the king corned beef. Wednesday, king chicken sub. Thursday, the king turkey. And Friday, the king tuna. And if you're hungry, I apologize for using this. But we want to write this relation. We could show this relation as an ordered pair. So just get my pen, make sure it's working. On Monday, that's your input. Your input's Monday. And on Monday, what's the special? What's the output? The king meatball. So I'm going to just say meatball. Sandwich. All right. The next day, our input is Tuesday. So on Tuesday, what is the related output? Is the king corned beef. And I'm getting hungry. And on Wednesday, our input Wednesday, the output is the chicken sub. And on Thursday, that's our input. And on Thursday, the output is the special of the king turkey. And then finally, well, Friday's the input. The output is the king tuna. So the relation is just the thing that assigns an output to a given input. So on Monday, the output is meatballs. The relation here is on Tuesday, corned beef. On Wednesday, chicken sub, etc., etc., etc. You will get more information regarding the vocabulary terms domain and range shortly, but on page 115, your author gives the definition for domain as the domain is all possible inputs of a relationship. Of a relation. And the range is all possible outputs of a relation. And like I said, you're gonna see more examples of that shortly. Please find parts A through F on page 97 of your math workbook. I'm going to work through these, and as I do, you're going to fill in your workbook. If you need to pause the video anytime, please do so. If you need to rewind and watch something that you've missed, please do so. All right, part A just gives us the information, the data. For the following relation, the input X is the ages of boys, and the output Y is the corresponding height in inches. Part B says, create a table of the X and Y values. So I'm going to do B up here, so I have a little room. What I'm going to do is just put my inputs of X there, my outputs of Y there, and I'm going to fill in my table. Not sure how many pieces of data I have, but when the boy is 7, their corresponding height is 41. And then I have a boy who's 8. Their corresponding height is 45. And then I have a boy that's 9. So I go that order pair. And this tells me the age. And then it tells me for that age, the corresponding height for that boy, 49. And then the next one, boy's 10. And that 10-year-old boy has a corresponding height of 52. And then the next boy, whose age is 10, has a corresponding height of 53. And then I have another one who's 11. And the 11-year-old has a corresponding height of 55. And then the last one, when they're 12 years old, their corresponding height is 59. So that's how you do that table of values that represents the input and the output of this data. Part C says plot these points on a graph. So unfortunately, I don't have a fancy pre-drawn graph, so I'm going to create one. And I'm going to have ages going along the horizontal axis and height going along the vertical axis. And I'm starting off at age 7. So 1, 2, 3, 4, 5, if I want, 6, 7, 8, 9, 10, 11, 12. All right, and then the heights, I'm going to do a little break here. That means I'm doing a break in my graph. And I'm going from basically 40 up to 60. So let me start here at 40. Let me do this. It's 50. I'm going to be doing a little estimating. This will be 60. So that's 55 and that's 45. And I'm going to be doing, like I said, a little estimating. So I need to plot 7, 41. So I go to 7 on the horizontal or x-axis, which be there's 7. Oops. There's 8, 9, 10, 11, 12. Just make it easy for us to see. And I'm going to go up to a height of 41, which would be like right around there. Because 40, my graph's going to get very messy doing it this way. That's okay. Then I have 845, so go to 8 on the x-axis, go up to a height of 45 on the y-axis. Then I have 949, so just going to be a little bit below 50, so I'm estimating. Then for age 10, I have 2 points along the vertical axis. I got 52 and 53, so I'm going to have 2 points basically right on top of each other. And then for 11 years of age, I have 55, which would be right around there. And then for 12, I have 59, which would be just below 60, so somewhere around there. So that's how I can represent the same data, the same relation, using a graph. You are basically plotting the ordered pairs, and where those points are, like right here is 8, 45. It tells you for 8 years of age, that kid has a height of 45. All right. D says copy and complete the mapping diagram. They give us the mapping diagram. It is right here. I'm not going to copy that again. And you don't have to either. But what I want to do is draw an arrow that connects the input in the age set with its corresponding output in the output set. This is an input set. This is output set. So 7, when the kid who's 7 has a height of 41, I connect them that way. You draw a ray connecting the input to its corresponding output. 8, when the kid's 8, 45. The kid who's 9 years old has a height of 49. Now we have two kids that are 10. One 10-year-old has a height of 52. The other 10-year-old has a height of 53. And then the kid who's 11 has a height of 55. And the kid who's 12 has a height of 59. Part E asks you to state the domain. I'm going to use these curly brackets to state the domain, and the domain are all the inputs or the X values. So 7, 8, 9. I use commas to separate them so I know I'm talking about different values in the set. 10 repeats. I have a 10 here and I have a 10 there. I only need to list it one time. I don't need to list that again. I have 11 and I have 12. There are all my inputs or all the sets of, that's a set of inputs that are in our domain. And F asks us to state the range of the relation. So we want to find all the elements of our range. And those are all the outputs. So you're looking for all the Y values. So all these Y values are part of my range. They're all my outputs. 41, 45, 49, 52, 53, 55, and 59. If any of those repeated, I would not need to include them. Just one time. Don't have to write multiple inputs or outputs. All right, that's it. We're going to learn a little bit more now about functions. Now that you learned about relations, let's find out what makes a relation a function. So what we're going to do is I'm going to play a video that does a very good job at not only describing when a relation is a function, but also the vertical line test.
Hi, I'm Rob. Welcome to Math Antics. In this Algebra Basics lesson, we're going to learn about functions. Outside of the realm of math, the word function simply refers to what something does. But in math, the word function has a more specific meaning. In math, a function is basically something that relates or connects one set to another set in a particular way. A set is just a group or collection of things. Often it's a collection of numbers, but it doesn't have to be. A set could be a collection of other things like letters, names, or just about anything. Sets are sometimes shown visually like this, but more often you'll see sets written using a common math notation where some or all of the members of the set are put inside curly brackets with commas between them like this. A set can have a finite or an infinite number of elements. For example, a set containing all the letters of the alphabet has only 26 elements, while a set of all integers has an infinite number of elements. Okay, so a set is just a collection of things, and a function relates one set to another. But how exactly does it do that? Well, to understand how functions work, it will help if we start by naming the two sets, the input set and the output set. A function is something that takes each value from an input set and relates it or maps it to a value in an output set. And you'll often hear these input and output sets referred to by special math names. The input set is usually called the domain, and the output set is usually called the range. And it's really common to see some or all of a function's inputs and outputs listed in what we call a function table. A function table normally has two columns, one on the left for the input values and one on the right for the corresponding output values. The function itself is often written above the function table and in the form of some sort of mathematical rule or procedure. For example, let's say that the input set of a function is a list of common polygon names like triangle, square, pentagon, hexagon, and octagon. The function itself could be a simple rule that says output the number of sides. That means if we input triangle into the function, the output will be 3. And if we input square, the output will be 4. If we input pentagon, the output will be 5, and so on. So this function simply relates the name of a polygon to its number of sides. That's cool, but most of the functions that you'll encounter in algebra will be a little more abstract than that. They'll usually just relate one variable to another variable in the form of an equation, like this one, y equals 2x. In this equation, if we treat x as the set of numbers that we can input, the domain, and y as the set of numbers that we get as outputs, the range, what we have is a very simple algebraic function. And just like the polygon example, we can make a function table to show some of the possible input-output combinations. For this function, we could choose any number at all for the value of x. But to keep things simple, let's just try inputting 1, 2, and 3 as values of x and see what outputs we get for our table. If we input the value 1, in other words, if we substitute the value 1 for the x in our equation, then we get y equals 2 times 1, which simplifies to y equals 2. And since y is our output variable, we put a 2 in the output column. Next, if we input the value 2 into our function, we get y equals 2 times 2, which means y equals 4. So the output value is 4. And last, if we input the value 3 into our function, we get y equals 2 times 3, which means y equals 6. So the output value is 6. See the pattern? For each input value, the output value is twice as big, which is what we would expect because the original equation says that y, the output, is equal to 2 times x, the input. Okay, so we've seen some examples of functions that relate inputs to outputs, but there's an important limitation about functions that we need to know. To understand what that limitation is, let's try to make a function table for the equation y squared equals x. Again, the x variable in this equation will be our set of inputs, and the y variable will be our set of outputs. Since y is our output variable, it will help if we first solve this equation for y, and we do that by taking the square root of both sides. But because of negative numbers, we need to take both the positive and negative root of x, since there are two possible solutions to our equation. But won't that mess up our function table? If we input an x value of 4, the positive, or principal root, would be 2. But we also have the negative root as a solution. If x equals 4, then y equals 2 and y equals negative 2 are both possible solutions to the equation y squared equals x. So in this case, for each value of x that we input into the equation, we'll get 2 values of y as outputs. Can a function do that? Upon review, the equation gave 2 outputs for a single input, therefore it's ruled not a function. You see, functions aren't allowed to have what we call one-to-many relations, where one particular input value could result in many different output values. One-to-many relations certainly do exist, as we can see from this example, but we don't call them functions. For something to be called a function, it has to produce only one output value for each input value. So a function doesn't just relate a set of inputs to a set of outputs. A function relates a member of an input set to exactly one member of an output set. The equation y equals 2x qualifies as a function because no matter what number you put in, you'll always get just one number as an output. But the equation y squared equals x does not qualify as a function because a single input can produce more than one output. Let's look at another simple algebraic equation to see if it's a function. Y equals x plus 1. Again, the x values will be inputs, the domain, and the y values will be the outputs, the range. Let's quickly generate a function table for a few possible input values, like the integers -3 through +3. If you watched our last video about graphing on the coordinate plane, you may notice that each row of this function table is basically just an ordered pair. It's an x value followed by a y value. We could even rewrite all the inputs and outputs in ordered pair form if we wanted to. And that means you can also graph all of these pairs of inputs and outputs on the coordinate plane. You can graph a function. Here are the points from our function table plotted on the coordinate plane. And here's the resulting graph we get if we connect those points. It forms a straight line, and it's an example of what is called a linear function. In algebra, there are lots of different kinds of functions that have interesting graphs. Quadratic functions, cubic functions, trig functions, and many more. These graphs may look like just a bunch of squiggly lines, but they're all functions. And we can tell they're functions just by looking at their graphs because they all pass the vertical line test. Remember how functions aren't allowed to have more than one output value for a particular input value? Well, the vertical line test helps us see if a graph has any of those one-to-many relations that would disqualify it as a function. Here's how it works. Imagine that a vertical line is drawn on the same coordinate plane as the graph that you want to test. Then, imagine moving that vertical line left and right across the domain, paying close attention to the point where the vertical line intersects with the graph. If that vertical line only intersects the graph at exactly one point for every possible value of x in the domain, then that means that there's only one output value for each input value. There's only one y value for each x value, so the graph qualifies as a function. Okay, so all of these graphs pass the vertical line test and are functions. But what's an example of a graph that doesn't pass the vertical line test? Well, here's one. It's the graph of our equation y squared equals x. The domain of this equation doesn't include any negative input values, so there's some places where a vertical line wouldn't intersect the graph at all, and that's okay. And there's one place where the vertical line would intersect the graph at just one point, which is also okay. But as we move to the right on the x-axis, you can see that our vertical line is now intersecting the curve in two places. That means this equation is giving us two possible outputs for some of its inputs, which means that it's not considered a function. Okay, now before we wrap up, we need to talk briefly about some common function notation that can be pretty confusing the first time you see it in math books.
So the beauty thing of watching this on video is that you could always replay something that you missed or want to go back and see. I just want to bring to your attention on page 116, your author has the following definition for function. A function is a type of relation in which there is only one output for each input value. And that's what Rob was talking about in his video, about that one-to-many cannot exist when we have a function. On page 116, you'll find example 1, and we're going to look just at part A. Now part A has all the information given to you. We're just going to quickly talk about it. What this problem is, what this data represents is the relationship of the number of students and number of classrooms that are being utilized at a school. So if I have 40 students, then 2 classrooms are being used. When we have 45 students, 3 classes are being used. And let's say we have a grade with 50 students, and they're using 4 classrooms. So this table of values is one way to demonstrate the relation of 40 students with 2 classrooms, 45 students using 3 classrooms, and 50 students using 4 classrooms. Another way or method to represent this data is using a graph right there, where each of these points represents the x and y value for your input and your output. So when your input's 50 students, your output would be 4 classrooms. The third way you could do this is a mapping diagram, where you have all the inputs, the set of all the inputs on one side, and arrows connecting each element or each value inside the inputs to its corresponding output. The domain will be all of the inputs or number of students. So there's our domain. Those are how many students we have. And the output is your range. So those are number of classrooms being used. And that's about it for this. Oh, very important. Notice how each input is going to one and only one output. That is a definition of a function. So when we have a mapping diagram that looks like that, we have a function. Now it's your turn to try one. Please go to page 118 and number 4. On number 4, you are asked to give the domain and range of each relationship and interpret them in context. State the corresponding outputs for the given inputs in context and explain what a relationship is a function. So, in the moment, I'm going to ask you to pause your video. Pause the video, work on it, and then come back, play the video again, and see how you did. Pause the video now. All right, welcome back. So, we're asked to find a domain. And the domain is a set of all the inputs. The input in this case be the time exercising. So it'll be 20 minutes, 30 minutes, 35 minutes, and 60 minutes. The range will be all of the calories that are burned, all the values of your output. So we'll have 50 calories being burned, 85 calories being burned, 85 again, but since I already wrote it down once, I don't need to write it again. We don't need repeaters. And then 100. And now, I'm not going to write this down, but we're supposed to state the corresponding outputs in context. So, when someone exercises for 20 minutes, they're burning 50 calories. When someone else exercises for 30 minutes, they burn 85 calories. A third person, when they exercise for 35 minutes, they burn 85 calories. And the final person, when they exercise for 60 minutes, burned 100 calories. Is this a function? Well, do all of the inputs, let me change something quickly. For each input, am I going to one and only one output? Well, there the 20 is only going to 50. The 30 is only going to the 85. The 35 is only going to the 85. They could both end up with the same output, but there could only be one pathway from each input. And the 60 only has one ray going to 100, so this is a function. Every input has only one output. All right, so let's see if these 3 graphs pass the vertical line test. The exponential vertical line test was given in the earlier video, so let's just see how this goes. Number 10, if I draw a vertical line test, anywhere I draw a vertical line, does my vertical line only touch the graph one time and one time only? Well, in this case, there is no vertical line that will touch the graph more than one time. So this is a function. In number 11, if I draw a vertical line right there, it touches it here, 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 and here. It touches that vertical line touches my graph more than one time. So this is not a function. It's just a relation. In number 10, it's a relation that is a function. And then number 12, going back, once again, if I draw my vertical lines, any vertical line will only touch this graph one time and one time only. So number 12 is a graph of a function. And we're almost done. It's your turn. On page 119, there's problems 6 and 7. Like you do is work on these problems. Pause the video before you work on them. When you're done, start the video up again and see how you did. Pause it now. All right, welcome back. In number 6, if I draw any vertical line, my vertical lines only touch my graph in one place and only one place. So number 6 is a function. A graph of a function. Now number 7. If I draw my vertical line right there, it touches my graph right there. But anywhere else I draw my vertical line, it touches it in more than one place. So number 7 is not a graph, that is not a function. Okay, that's it. Hope you got a decent understanding of this. If you have questions, ask your teacher in class. All right, have a good day. Bye-bye.